Okay, folks, so this is our new content that we're going to try these videos for. Again, the slides are up there, but if you want the video explanation, thought I'd provide that. Okay, so we're doing t-tests with independent samples. I'm going to go through the, the slides within the video somewhat fast because you have the slides, so I don't want to make this video too long, so I'm going to go too fast, arguably, on this. Okay. So basically what we've been doing in the z-test and the t-test is up there. Z-test, we were comparing to a population mean. T-test, we were doing the same thing, but where we didn't know the population mean, and we used sample means and sample standard deviation that led us to things like the estimated standard error. Okay. Most of our tests are going to involve two or more groups. Okay, so students in 406 are going to design tests where they have things like the experimental group and the control group. Okay? So that's what this test is going to show us. Independent samples just means two groups. Okay? It could be, there's two ways of doing this. We're focusing on the first way within this unit. We're going to take our exam later. And then the first chapter of the fourth unit is going to be this way with a repeated measures design. Okay? But set that aside for now. We're just talking about the independent measures, the between subjects. We have two different groups of people. One group gets the control, one group gets the experimental. One group gets cupcakes, one group doesn't get cupcakes. Okay? Because of this, we basically have two of everything now. We don't have one sample mean and one population mean. We have two sample means, two hypothetical population means, two samples, two sample sizes, two sum of squares. Okay, so what you're going to see when we start to get into the formulas in a second is that it looks like we have double everything because we do. Okay, so what we're doing is saying, are these two groups different from one another? If we compare the mean of one, counting for things like the sum of squares and the variance, if we compare the mean of one to the mean of another, are they different? The null says there's no difference. The mean of one minus the mean of other, 0. The alternative says they're different. Okay? This could have direction, or it could just mean that there's a difference. Okay, so last time we're using this first formula. Sample mean minus population mean over the estimated standard error. Again, we have two of everything. It looks like this, but really we ignore this part of it. It's sample mean minus sample mean over estimated standard error. So it should look relatively familiar. But to get to this piece, we have some more math coming our way. Okay? So again, we're using the same basic idea. We need to find estimated standard error. In order to find estimated standard error, we have to do something new. Okay? And that new piece is that we need to find what is the variance for both of them. Okay? Before, when we found estimated standard error, we did some version of this. What's the variance over n? You might think, oh, we can do variance over n for both of them and sort of add them together. Yes, but no, we can't do this. Instead, we have to calculate something called pooled variance, where instead of finding each variance separately, we're going to combine them together. Okay? So the only way this formula works is if we have samples of the same size. Okay? What it's going to do, if we don't have the same size, is it's going to get closer to the one that's a larger sample size. If you think back to when we had factors that affect whether or not we're going to reject or fail to reject, we said as n goes up, the chance of rejecting the null also goes up. Okay? As n goes up, standard error goes down, chance of rejecting the null goes up. Okay? So larger samples are more accurate, and so if we don't have the same sample size, we can't use that formula. Instead, we use pooled variance. Pooled variance, just like this, right? I told you we have two sum of squares, two ends. We also have 2 degrees of freedom. So pooled variance is not too bad, right? Remember when we were doing variance before? Sum of squares over df? We have 2 of them. Sum of squares 1 plus sum of squares 2 over df1 plus df2. The reason for combining this into pooled variance is that we want a larger sample to matter more. And you're going to see that with some examples in just a second, I promise. Okay, so you're going to use pooled variance instead of variance. What this also means, you can see that within these examples. Okay, so these are the same sample size. Both of them have 9. You might say, wait, it says 8. That's df. Both have 9. And when we go to find pooled variance, doesn't matter which way we did it, right? If we found them separately or together, it splits the difference because they have the same sample size. Okay. When we go to do this with things that are different sample sizes, this one has 11, this one has 8, it's going to be pulled closer to that variance within sample 1, that is 5, than the variance of sample 2 of 10. So when we do pooled variance, we get 7.06, not halfway between. Halfway between would be 7.5, but it's closer to 5 because that one has a larger sample. Okay? If we keep this going with another example, we have sum of squares, we have df, we calculate this. Again, this one is double the sample size. Well, not quite because it's 7 and 13, almost double sample size. And so when we calculate the variances separately, which we're not going to do except for demonstration purposes, we get 21 and 16. Yes, I'm rounding. Pooled variance, 125 plus 190 over 6 plus 12, 17.5. It's a lot closer to that one because it has a lot larger sample size. Okay. So where is this going? Pooled variance, what comes next? Well, the estimated standard error comes next. Okay, so that's the next piece of this. You can sort of ignore this part of it, but it's S subscript M1 minus M2 equals square root of pooled variance over n plus pooled variance over n, right? If I hid 1/2 of this, it should look familiar. Estimated standard error, square root of pooled variance over n. Now we have 2 of them, and we're using pooled variance instead of each separate variance. Okay, so this allows us to get the estimated standard error, and if we go from estimated standard error, we're going to do a t-test next, and that's what we get to at the end. Okay. Again, it shows it double because we have population mean difference, but we have already sort of hypothesized that's 0. So in essence, it's mean 1 minus mean 2 over estimated standard error. And again, we got that from using pooled variance and then the estimated standard error. Okay. Just real quick, the t-critical, the way we do it, we find the df of all of it. So if we have samples of 20 and 25, 20 plus 25 is 45. We're going to subtract 2 and get 43. That's what I'm showing here. You could also take 1 away from each and add those together, whichever way you want to do it. This is just the sort of notation form. N1 minus 1, that should be N1 minus 2. Minus 1, let's fix that. Or N1 plus N1 minus 2. Okay. Again, you can find this within some examples. We have 8 and 13. You can find the df of 19 and then the corresponding t-critical. Same way we did for the other t-test. You just go to your t-table. Okay. Same thing down here. df is 18 if we have 3 and 17. What a strange unequal sample sizes. This will be the last slide within this video. I'm trying to put it all together. Okay, so single sample t-statistic we did before. We had sample mean, population mean, estimated standard error. But to get that kind of going this direction, we defined sample variance, sum of squares over df, use that to find the estimated standard error, and then did m minus u over estimated standard error. Independent samples or independent measures t-test. We have 2 sum of squares, 2 df's, put those together to find, this was variance, this is pooled variance. So it will be pooled variance. And then we use pooled variance instead of each separate variance, accounting for unequal sample sizes, to find our estimated standard error. It's all in a square root. It should look familiar. This part we can sort of ignore because it's going to be 0. So it's m1 minus m2 over whatever we get from the estimated standard error. We get a t. We compare that to a t critical from before. Then we say, do we reject or fail to reject? And we draw our conclusion, same as before. Okay? And I'll make another video to show what this looks like within some examples. Thanks.